Hey, Steps.
Sisters.
I'm Lasya.
And I'm Kritika, and we're your trainers from Future Steps.
Today we'll be understanding matter. It's the physics introduction for grades 5 to 7. You know that matter is everywhere around us. So join us on an exciting journey to explore matter. Anything that has mass and takes up space. We'll discover different states of matter, observe how it changes, learn important physics laws, and conduct fun experiments.
Okay, so let's get started. Now, what is matter? This is just the basics. We've probably already gone over this, but just as a type of review, let's go over it again. And this is more in a physics kind of way of defining matter, because usually when we define matter, we just go solids, liquids, and gases. And now we're going to talk about factors of it that is useful in our physics world. So, like Lassia said, matter is everything about around us. So, everything around us that has mass, which is measured in grams or kilograms, is matter. And everything around us that takes up space, that means it has volume, is also matter. And then matter is made of tiny particles called atoms. These atoms combine to form molecules, which build everything from air to zebras. That's an interesting comparison. Airs and zebras. Yep, at least it'll help you guys remember.
Now let's look at different states of matter and particle movements. So we have solids, liquids, and gases. Solids, particles are tightly packed in a fixed arrangement. They have fixed shape and volume. Particles vibrate in place. They cannot be compressed easily. Examples are rock, ice, and wood. It can even be a water bottle, not including the water, but just the water bottle itself. And then we have liquids. These are particles that are close but can move past each other. So they have no fixed shape and they take the shape of the container they are in. They have a fixed volume and particles slide around each other. Examples could be water. This is where water comes in. And then we have milk, oil. You can also say shampoo, anything that's liquidy.
Hmm.
Then we have gases. These particles move freely with lots of space between them. So they have no fixed shape or volume. They fill entire container, like they move around really freely and they move around in different directions. And the particles move rapidly in all directions. Examples are air, helium, steam, and so on.
Okay, now let's talk about physical and chemical changes in matter. So, physical changes would be if it changes form but not composition. For example, when you pour water from a water bottle into a glass, it changes form as in it it looks well, it changes form as in like not just pouring it from a container to another, but like if I put water into a pan and then I like heat it up, it's going to start evaporating. So it's changing its form from a liquid to a gas. And then if I cover it up or like cool it down, then that gas is going to turn back into a liquid. The same goes if I like pour water into a container and then put it into a freezer, it's gonna form ice. So it's gonna change from a liquid to a solid. And it can usually be reversed, like how I talked about the evaporation, going from evaporating and then going back into a liquid. And an ice cube also melts. So an example of these physical changes would be something like melting, freezing, dissolving, evaporating, condensing, etc. And then So try this. Dissolve colored drink mix in water. The color spreads, but it's still the same substance. So what that means is like if you take water and then you just put in like a drop of paint or something like that, it's probably gonna spread in the water slowly and the water is gonna change its color, but it's still water. So if like the water becomes orange, it's not gonna turn into orange juice, right? It's just changing color. And then chemical changes would be if it creates new substances with different properties, which usually cannot be reversed and often shows signs like bubbling, color change, or heat, or like smoking or something. Especially if it's bubbling, that's one that's like one very common way for you to be able to see that. It's and it looks pretty cool, but it's definitely dangerous, so do not try that at home. But there is one thing you can try at home. So mix vinegar and baking soda and see bubbling as a new substance. And that new substance is carbon dioxide gas that forms. So this is this is what I used to do. So I used to I used to put color in my vinegar and so okay, so what I used to do was I would put a couple drops of color and then put baking soda on top of it. So red color and then baking soda on top of it. And then I would pour a little bit of vinegar. That way it starts bubbling up and it looks like lava. And that's how I made some of my volcano projects. So you can also try that and it's pretty cool. But first do try looking at the bubbling reaction and then you can try out these experiments.
Now let's look at conservation of matter. So there's a law for this, and that is that matter cannot be created or destroyed in a closed system. It can only be changed from one form to another. This this is important, and this law means that mass before change equals mass after change. So mass will always be the same. It cannot be created or destroyed. It can only change from one form to another. So atoms rearrange, but they do not disappear. That means if they do disappear, that means they're getting destroyed. And that's impossible according to the law. And works for both physical and chemical changes. So this law does work for both chemical and physical changes too. Antoine Lavoisier discovered this law in 1700s. He often used the father he often called this the father he was often called the father of modern chemistry. So he discovered this law. An experiment you can try to actually test this out is balloon inflation. So firstly, put in baking soda in a balloon. Fill bottle with vinegar and attach balloon to a bottle without mixing yet. So just attach it on top and then weight the whole system right before you put the actual open the balloon into the bottle. Just weight it, like holding the balloon apart from touching the bottle itself, and then lift the balloon so that it can mix with the chemicals. It means the vinegar in the bottle, and then it will inflate. So this means that the balloon will get bigger due to the release of due to the mixture of baking soda into vinegar. It releases carbon dioxide and air, which indeed expands the balloon, giving it air to fill in the balloon and making it bigger. So what's your last step is weight it again and see if it's the same mass. And it should be the same mass because that means, and it totally proves the law that mass before change equals mass after change. Make sure to when you're weighing in the last step, make sure to weigh the balloon with the gas too.
Okay, so now we're going to talk about Newton's laws and matter interaction. We did have a video about this earlier, so you guys can go back and watch that for a more detailed explanation of the Newton's laws. I'm pretty sure that was the fourth video that we did that we have uploaded, and you can probably watch that. So now let's get into this. An action force. So when you push on matter, you exert a force in a specific direction. For example, when you push a door, or when you throw a ball, or when you're jumping off the ground, you're exerting force. And then there's Newton's third law, which is force of an action equals the opposite. So force of an action should equal negative of force of the reaction. So that basically means that for every action there's an equal and opposite reaction. So the negative is supposed to show the opposite part. And remember that forces always come in pairs. So if you apply a force, then whatever you're applying a force on is also applying a force on you. And then there's a reaction force, which is that matter pushes back with an equal strength in the opposite direction. For example, the ground pushing up on your feet, or the rocket pushing exhaust gases. So you can see how action and reaction force work together. So the action is that you're jumping off a ground, and the reaction is that the ground is pushing up on your feet. That is why you're able to jump. Because when you're jumping, you have to push yourself down to be able to jump back up. And that is where Newton's third law comes up.
Now we're going to talk about a fun physics experiment with matter. One of the experiments is crushing a plastic bottle. So put a small amount of hot water in a plastic bottle, cap it tightly, and let it cool. Watch as the bottle crushes itself. Why does this happen? It's because cooling gas particles slow down and take up less space, creating lower pressure inside and making the bottle crush. A second experiment you can try is making butter. Fill a jar halfway with heavy cream. Seal tightly and shake really hardly for 10 to 15 minutes. And watch the liquid transform into solid butter. Why does this happen again? That's because physical agitation separates fat yeah, globules from liquid and binds them together, making them from heavy cream into butter. So heavy cream is kind of like a liquidy solid texture, and butter is totally like a solid, creamy texture. And finally, you have the balloon expansion. Place a balloon over an empty bottle's mouth. Put the bottle in hot water. Make sure you have adults help with it if it's too extreme hot water. And watch the balloon inflate. So why does this happen? Heating increases the gas particles' motion, so creating higher pressure that inflates the balloon. As as much as the temperature increases, the movement of the gas particles also increases, making the balloon expand and inflate.
Mm-hmm. Okay, so now we're going to talk about a few key equations and laws about matter. Let's start off with density. So the density equation is density equals mass over volume. Notice how that's a capital V, so capital V stands for volume, and lowercase v stands for velocity, so don't confuse the two of them. So, and this thing right here is what represents density. It's called rho. So here The rho represents density, m represents mass, and capital V represents volume. This explains why some objects float or sink. Because think about it, if the density of an object, so if we put a rock in water, it's going to sink down. That is because a rock is denser. And why is that? That is because a rock has greater mass. And even if it doesn't have greater mass, it possibly has a difference in volume that makes its density higher than water's. And water does have a specific density you will that you will be given for every question because that's how they do it. And the density of water is a constant thing until the water has been diluted or something like that, which is not usually the case. And then there is the conservation of mass, where the mass before any change equals the mass after, like Lassie had mentioned earlier. So in a closed system, when we say closed system, we mean a system where no outside force acts. So there will be no friction, because if there's friction or any force like that, then it can it can definitely change a few of these things. So in a closed system, the total mass remains constant during any physical or chemical change. And then there's Newton's third law. If you did watch the force video, then when I told you that this equation is going to show up a lot, this is what I meant. Because I think this is the second video I'm mentioning this in. So do remember this law because it is really important. So Newton's third law basically says that the forces between two objects are equal in magnitude and opposite in direction. That means that so basically this this pen, if it's kept on my table, then there are two equal in magnitude forces acting on this. One is gravity, and the other is the table surface acting on the pen. So one is the pen acting on the table, and the other is the table acting on the pen. And they're both equal. That is why the pen is not moving. And that this is only true if the object is at rest. Because if it is moving, then there will be a couple differences. Because to be able to move this up, one of the forces has to go down.
And here are some questions for you to test your knowledge. Number 1, states of matter. What are the 3 common states of matter? Describe how the particles move in each state and also the differences of the particles. Number 2, changes in matter. Explain the difference between physical and chemical changes. Give an example of each. Number 3, conservation law. What does the law of conservation of matter state? How could you demonstrate this? Number 4, Newton's third law. Describe the Newton's third law in your own words and give an example from everyday life. Number 5, and lastly, the balloon experiment. If you inflate a balloon using a chemical reaction inside a closed bottle, what happens to the total mass of the system? And why does this occur? Okay, so before we go on to the answers, make sure to pause the video right now before you check your answers. Make sure you take a notebook or a piece of paper and answer all these questions. And also, the answers that we are going to give you later may not be exactly the same answers you have, since you're going to give your own examples and you're going to explain these in your own words. But make sure you got the main point through. Like in our answers, we're gonna show you later on. We have some main key points that we want y'all to mention. Make sure you mention them, and if not, just correct your answers and revise them to get better at it. Now pause the video now and answer these questions.
Okay, so hopefully you paused the video and you're back to this video now. we will be going over the answers. And yes, we have already typed the answers out because it will take a really long time if I type them right now. So let's go ahead and see the answers. Okay, so for the states of matter, there are three states of matter: solids, liquids, and gases. In solids, the particles vibrate in fixed positions. So for a solid, the particles will look something like this. So we have like a tight. Okay, I don't know why this isn't letting you write. This is how it's probably going to look like in a solid. And yes, my computer is not the best for physical writing things. Okay. So it's all tightly compact, and there are still spaces. So like you see a space here, and then there is a space here, and there's a space here across. So there are spaces, but they're really small. So that's what makes it really tight. So then we have liquids that are particles that slide past each other. So in liquids, the so liquids look somewhat like this, where yes, the particles do collide with each other and with the walls of whatever container they're in. And then we have gases. Gases are particles that move freely in all directions, so gases would look something like this. And notice how your gases are moving freely anywhere. So they could dash into each other, they could dash into the walls of the container they're in, or anything at all. So they're gases. You can see some gases and you cannot see other gases. For example, our air, the air we breathe, you can't really see it, but it's all around us, right? Now we're going to look at the changes in matter. So the changes in matter of physical and chemical is, let's think about physical first. So physical changes in matter are changes that occur without changing the substance. So but only changing the form of the substance, but not the actual properties. And what we mean by changing the form is so let's say I have a cup of water, and then I put it into a ice tray and I freeze it. It's going to turn into a cube of ice. So that shows a physical change because it just changed in its form. It went from a liquid to a solid, but it didn't actually change its properties. It's still it's still water. It's not really it's still water in a different state. And then chemical changes, on the other hand, are where new substances form with different properties. So so different properties would be something like rusting or burning wood, or you know, like how we talked about the vinegar and baking soda thing, where you can look at the bubbles. So every time there's a chemical reaction in rusting, on top rusting happens on top of iron metal, right? And this can happen when this happens. So if you leave your iron rod in water and you come back later, you see rust, you're probably going to question, oh, well, where did this come from, right? It didn't exist earlier. So a chemical reaction occurs that causes this new substance to form. And then when you're burning wood, you release a lot of carbon dioxide is released from the fire. And there are also many other examples. Now we're going to talk about the conservation law. So in the conservation law, it says that matter cannot be created or destroyed as long as it's in a closed system. And it and matter can only be changed from one form to the other. So that also means that the mass before any changes should equal the mass after. And remember that it's always in a closed system. Because if it's not in a closed system, then matter can possibly be destroyed. So most of these things will be in a closed system because in physics we neglect a lot of real life things so that we can answer questions. Now let's talk about Newton's third law. Newton's third law says that for every action, there's an equal and opposite reaction. So for every action force, there will be an equal and opposite reaction force. For example, when you're swimming, you push the water backwards, and when you're pushing on the water also pushes on you. So that's how you move forward. And then let's talk about the a balloon's mass, right? So the total mass stays exactly the same because matter is conserved within a closed system, and it is within a closed system unless and until there's an external force acting on it, which we will not have ever until higher levels of physics, so you don't have to worry about that just yet. And then the atoms do rearrange, but they don't disappear. Because remember, there's the conservation law, where matter cannot be created or destroyed, and it's in a closed system, so nothing can just leave or come or just appear out of nowhere. So that's why the total mass should stay the same. It's because of both the conservation of matter and the conservation of mass. So here there can be two answers accepted. That could be because matter is conserved, or you could say because mass is conserved. And I am trying to write that. Those are the two reasons. And the reason why mass is conserved is because matter is conserved. So the better answer choice would be that matter is conserved and it's in a closed system, so the atoms don't disappear or appear, they're just rearranged. So that's all we have for you today. I hope you enjoyed this video. We hope that you keep practicing these questions, do more questions like this, and if you have any questions about anything we discussed this entire video, you can comment down below. And you can also comment for any video suggestions or anything like that. And we do check all of our comments, so we will likely check this. So hope this was useful. If it wasn't, do comment down below so we know. We love criticism, and criticism equals growth. So you guys should love it too. Now, our amazing physics geniuses, I'm pretty sure you guys are doing pretty well with this, so continue practicing as much as you can because physics is all about practicing. Because the more you practice, the faster you can remember all these equations and all of that, and all of the laws. So that's all we have for you today. See you in our next video, Stepsters. Goodbye.
Bye, Stepsters.
Bye.